here is homework 7 for statics, and we're doing problem 1. A window in the new Hart building has a crank to open it arranged as shown. The dimensions are 2 inches, so it's 2 inches long right here. 3 inches right here. It's 1 inch, and this is arranged at 30 degrees. It makes an angle right here at 30 degrees. The vertical force is 1.8 pounds, and it's applied right here. Determine the magnitude of the moment about segment AB. So here we go. We'll write out all this regular stuff. And this is, spring of 21. And let's see, this is ES110. And this is homework number 7. I have to pause this because my boss. Okay, that wasn't worth it. All right, so we have problem 1 right here, and I'll do a little sketch with my handy dandy ruler here. Don't need to make a crazy sketch as part of this, but we do want to convey what the problem is in case some archivist in ancient times comes by and they want to know what the civilization was doing with this piece of paper. They won't know what this piece of paper was for if we don't give them an idea here. So, in the interest of mankind and history and whatnot, we want to make sure that we're giving a sufficient amount of information for those later people, the people to come after us, who will take a look at this documentation that we're providing, and so they can know what our culture was like. All right, let's see. In terms of distances, let's see. Boom, boom, and trying to make all of those distances right there. And there's going to be a little bit of a challenge in here. I got to wonder if people are going to pick up on this, but that's okay. It's a little bit more difficult than you might think. I think so. Let me see. I have a feeling people are going to oversimplify it, and I'm starting to think that I have previously oversimplified it, but let's check it out. Let's see. All right, so there's D happening right there, and this is the force at D. So get rid of this, or make this a little bit shorter. And I'll have this as LAB, and this is going to be LBC, and this is going to be LCD. Okay, well, we have a few things we have to take care of right here. We could maybe overly complicate this, but let me give the givens. And we're told that we have LAB is 2 inches, LBC is 3 inches, LCD is 1 inch, and FD is 1.8 inches. And we want to find the moment about AB. Right? So let's try to get this all put together. The first thing we want to do is get a position vector, I think, that goes between A and D. So we want to find the position vector that is D with respect to A. This gets a little complicated because of the angles involved right here, right? So we want to maybe take a look right through here at what's going on right there, okay? By way of drawing this thing out right here. You can see that I'm trying to do parallel right there. That was not a good job of parallel. Here's my parallel right to there, to there. Okay, so in the x direction, we're going to have LAB times the cosine of theta, and we're also going to have LCD times the cosine of theta, right? So really it's going to be LAB plus LCD times the cosine of theta. So that's going to be, let's see, 2 plus 1 times the cosine of, oh, we were also given this. I didn't write that down. That was going to be 30 degrees, right? So I'll put it down in here. Just cram them in there. 30 degrees. 30 degrees. I. All right, so, and in the y direction, we're going to have, once again, that's going to be 2 plus 1 times the sine of 30 degrees, right there, right? J. And now in the z direction, though, it's going to be entirely LBC because it is completely in line with this right here. So it moves it, and it's going to be the negative direction. So it's going to be a negative 3K inches. So let's write out what those values are going to be. So we have 3 times cosine of 30, cosine 3 times. All right, so that should be 2.598 I. And then this one is going to be 3 times the sine of 30, so that should just be 1/2 of it, right? Sure. So 1.5 upwards. And then we're going to have just negative 3, inches. It's supposed to be a K. Now we take the force at D as a vector, and that's going to be a negative 1.8 J pounds. We have a choice here. We could we could do this in order of operations, right? So we know this right here. Another thing we're going to need to know, by the way, is the lambda that's coming along this length right here. Right? So it's not going to be incredibly hard to do. It's going to be so let's get the position vector, and I think it's best to go from B with respect to A. So we'll have RB with respect to A. It's going to have a lot of the similar things, but not exactly. So we're going to take 2 and the cosine of 30, right? That gets there in the horizontal direction. And I plus, we're going to take 2 times the sine of 30, J, and that's going to equal, and this is all kind of weird, just, we'll see here in a second what I mean by that. We'll take 2 and 30 cosine times, so we get 1.732 I plus 2 times 30, and this should just be 1, duh. This should be 1, right? And these are inches, but we want the lambda. So we get the magnitude of this. We already know the magnitude. The magnitude is 2, right? That's the length of this thing, right? So the lambda B with respect to A that we would have is just going to be 1.732 divided by 2 the length I plus 1 divided by 2j. So that's just going to be, this is just the cosine of this angle right here, right? Cosine of 30. And this right here is just going to be the sine of 30. But thought we would go through it. And oh, and by the way, plus 0k. Right, nothing in the k direction onto there. So if we're going to do this in the order of operations, the thing that we would want to find, right, so we could write this thing out, is MAB is going to be lambda b with respect to A dotted against R d with respect to A crossed with F d. Right? So what that ends up being, okay, well, let me do this right here first. Let me do it in 2 stages, I think. I think that's how most students would do it. We could write it out actually as a 3x3 matrix right here, or we could do this in 2 steps right here. So let's do it in 2 steps because this is our introduction to the thing. But later on, we might want to do it in 1 step. So I'm going to take and find the RD with respect to A crossed with my FD first. Whoops. I need to move this keyboard over to the side. So I take my I and J and K, and then I take my position vector right up here, and I take a 2.598 and my 1.5 and my -3, and then I take my force vector, which is going to be 0, -1.8, and 0. And there's going to be a lot of zeros involved in this, right? It's really, so, and this probably is going to be, we'll see, but we'll see. Okay. So we take this and I'll write it out this way here. We take the I and we're going to cross this right here. So this is going to be 1.5 crossed with 0 minus -3 minus 1.8 right here, right? So there's going to be I. Oh, now I always do this wrong. Minus, this minus in this next one. Minus, take the J, but we're going to cross that against a 0 and that against a 0. So that's going to be 0J right there, right? Now plus for K now right here, we're going to do that cross with that and that cross with that. So we do have something here, 2.598, right? And that's going to be minus 1.8, and then it's going to be minus, and then it's going to be 1.5 times 0, 1.5 and 0 right here. So we have K, and those would be like inch pounds, by the way. And so what we're going to find right here is we're going to negative, so that's going to be a negative 3 times 1.8, boom, a negative 5.4 I plus 0J right there, which kind of makes sense. There's no reason why it would be spinning around the y-axis, so that makes sense. That's not going to cause a moment there. And then this one is going to be negative, right? Because that's positive, that's negative. Okay, so that's going to be our 2.598 times 1.8, boom. So we get a negative 4.676, and this is K, and these are inch pounds. All right. Now for the second step of this is we're going to take this guy right here, which, by the way, we could have called this right here. I could have called this the moment about A, right there, right? That was the moment about A. So we could say this is the moment about A, and these are all the moments about A. Now we want to find the moment about AB. It's not a vector because we're going to dot product it, B with respect to A dotted against MA. Right, so dotting the thing, we'll write it out, all the different things, right? So that's going to be this in the x direction, or 0.8660, against this in the x direction, -5, right there. Then it's going to be this in the y direction times this in the y direction, 0, and then take this in the z direction, and then this in the z direction. Right? So what we end up with, right there, MAB is going to be equal to this, just this right here, because that's 0 and that's 0. So all we're left with is a 0.8866 times, and we end up with 4.676 inch-pounds is the answer. Oh, and it's negative, right? So what does that mean? The negative, all right? So I'll accept either way, positive or negative onto here. But what it's essentially saying is, if we zoom out right here and we come back to the thing, I drew a vector that was pointing out that way, outwards. I went from B to A, right? B with respect to A. So I went from A to B, I should say. So I was going that direction by pointing that way. If I had gotten a positive, it would have gone this way. Instead, it's coming this way, which makes sense because this force is going to turn it that clockwise about this axis. I think this is a good problem because you could actually picture what's taking place here and some of the purpose behind it. Is there a shorter way to achieve this? I think if I took this force and I only took the component of it that was perpendicular to this line, and then I just multiplied it by this length right here, because that's the only thing that's causing a twist about this, is this length. So I want to get this distance and this force perpendicular. So what I would have done is I'd taken the cosine of that force and multiplied it by this distance. And I think maybe I would have gotten the right thing right there, right? So if that force is 1.8, and by the way, I think this angle right there was 30. The 1.8, and I take 30 and the cosine of that times there, and I was just multiply it by my 3. Yeah, I'd get the same thing, right? Simple enough, but while we can see if we had much more complicated arrangement there, we could go about and systematically find the vector, find the position vector to that way off distant complicated thing, get the moment, then have some axis that was not, we couldn't really get a gut feel for it. We could take it and we could dot product the moment that we got, and we'd be fine. So there we go. That is homework problem 1. 20 minutes.